Welcome, I'm Dr. Wood with the Citadel Civil Engineering Department. This is CIVL203 Dynamics, Learning Objective 4.4, Rigid Body Plane Motion Acceleration. In this video, we hope to define the rigid body plane motion acceleration, as well as dependent motion relationships for contact surfaces, as well as discuss the formulation of the rigid body plane motion acceleration kinematic equations using relative motion translation and fixed axis rotation equations. That's what we've got going. We are in Chapter 15 of Beer and Johnson's Dynamics textbook, looking at rigid body kinematics. First thing we want to note is that we have discussed plane motion as the superposition of translation and rotation. And so as we go in today's lecture, we're going to have exactly the same behavior. And so with that in mind, I'm going to stretch this screen over a little bit. I can do that. And so, and put some notes on the board for you. So the idea is that we're talking about plane motion acceleration. Get the spelling right. Acceleration. Plane motion acceleration. And when we talk about plane motion acceleration, the idea is that we're going to be working in 2D. So let's say I was to take an object, say, your average everyday tomahawk, and chuck it. What would happen is that we would see it translate, moving from side to side, as well as rotating. And so as we think about this, we recognize that we can use the same concept of superposition that we talked about originally for velocity. And when we use superposition, we're going to be taking calculating a general case by summing the translation and rotation cases for the problem. So we're going to break the problem into two pieces, one looking at pure translation, so what it would look like if our tomahawk was just simply translating, and then another one looking at pure fixed axis rotation, saying what if it was just rotating about some known point. So that's how we're thinking about these things. So we're superimposing these two things. So the easiest one for us to talk about, of course, is translation. And so if I were to have my tomahawk, I could draw it something like this, and I could call the location of the handle down here A, and the head up here B. And if we set at some particular motion in the flight of this object, we know the acceleration at A. If we're assuming it's just pure translation, that means we also know the acceleration at point B, because for a translating object, the accelerations are the same at every single point. This is what allows us to do particle motion calculations, looking at common accelerations between the 2 points. So, translation. The idea that we've got acceleration at A that we know, then we automatically know what the acceleration at the head is, point B. But for our general motion, the tomahawk isn't, if we throw the tomahawk, isn't just translating. It's also rotating. And so when we look at the rotation component, we're going to take our known location of rotation, which is down here at point A, around the handle, and point B, up here where the head is. We're going to think about it accelerating. So we can draw the acceleration in any old direction we want, though technically using our right-hand rule, the acceleration, as I've drawn it there, is negative. And that's okay. We'll also have an angular velocity going on at point A. It's important for us to be able to calculate our normal component of the acceleration. So the idea is that we're saying, okay, we've got the translation, now we got the rotation, and it's rotating about a point we know it's acceleration. It's accelerating with some acceleration like so. So if we look at these components, we're going to come up with two components for the acceleration at point B with respect to A. So we're standing on point B, we're looking at it back at A, we're trying to figure out what our motion is. We're standing at point A, looking at B with respect to A. We might have a position vector R, B with respect to A. And if we think about alpha, that's going to cause a tangential acceleration. So some portion of it is It's going to be tangentially accelerating. And in this case, alpha is negative, so our right-hand rule says alpha cross r gives us that tangential acceleration. And what I've done here is I have used the right-hand rule to come up with my directions. That's what you saw me do right there. Negative for alpha, cross r, thumbs pointed in the tangential acceleration direction. And then I just have alpha times r as my magnitude. In addition to the tangential acceleration, we're going to have normal acceleration, which is negative omega squared r. Now that negative means it's going to point back toward the center. And so our normal acceleration is equal to omega squared r with respect to a, like so. So we've got the translation component right here, right? So that's the translation. And then we got the rotation component like this, right? And we see that when we rotate it, our rotation component gives us both the tangential rotation, alpha cross r, or a times r, or alpha times r, angular acceleration times the position vector b with respect to a, and the normal component, negative omega squared r, or omega squared r b with respect to a, pointed back toward the center. In order to get our general case, we're going to use this idea of superposition. So we're going to add the two together so that we can come up with what is the general case, the acceleration at each location. So what we're going to do is we're just going to look at point A, and we're going to add the things that we see at point A to our general case at point A. So I have the acceleration at A here. I know something like that, acceleration at A, and I've drawn an alpha, and I've drawn an omega, so I can calculate my normal acceleration. So acceleration at A, my angular acceleration and velocity, angular acceleration and velocity, we have everything we need there. The next thing we'll want to do is we'll want to do the same thing for point B. Now point B is going to be more interesting because up here at point B, we have three vectors we're going to have to add together. And so what I like to do is use a force polygon to add those up. Alternatively, we'd be breaking them into their x and y components as we add them. That'd be the mathematical way we would do it. So the first thing we'll start off with is our translation component, the acceleration at A. Then I might add to it the radial component, or the tangential component, alpha r b with respect to A. So there's my acceleration at A. Now I've got my tangential component, alpha r. And then I would add my normal component, something like this. Whoop, no, it's got to be parallel. See if I can do this. Something like that. This would be omega squared r b with respect to A, which means that at this moment, this is my total acceleration for point B. I'm using a force polygon or an extension of the force triangle rule to do my vector addition, going head to head, tail, head to tail, head to tail, around the force vectors as I add up these three different vectors. So this diagram represents the addition of these three things. I can use this to come up with my overall equation. So my general form of the equation is going to say that the acceleration at point B is going to be equal to the translation component, acceleration at point A, that's up here, plus alpha cross r b with respect to A. That's the tangential portion of my rotation, minus omega squared r b with respect to A. That's the normal component of my acceleration. So when we look at this generalized equation, we've got our translation component. We have our, this would be our rotation in the tangential direction. And then this is going to be our rotation in the normal direction, like so. So this gives us our kinematic relationship for plane motion acceleration. It shows us that we can add the translation component at some known location to alpha cross r to give me my tangential component of the acceleration, plus omega squared r give me the normal component of the acceleration. Use vector addition, either using a 2-scale force polygon or breaking them into their x and y components and adding them up. Either way, that will work. So as we think about this, we now have this set of tools to handle plane motion acceleration. Now, this looks very much like what we did for velocity when we first introduced superposition of translation and rotation to get the general velocity relationships. There is no instantaneous center of rotation equivalent for acceleration, which is unfortunate because this is going to be fairly time consuming. You always have to draw 3 diagrams. You always have to collect up and write the equations for each point. Now, that said, we also want to talk about dependent motion for acceleration. And so if we look at our slideshow here, we'll remember that we talked about gears and contact surfaces. And when we talked about our contact surfaces for these dependent motion equations, dependent motion for contact, no slip, we said that we would have common tangential kinematics. That means that if we were to look at the interaction between 2 gears, pretend those were actually round, where they touch, they would have common tangential components. So we'd have a tangential direction that looks something like this, right? In the tangential direction. And in the case of velocity, all of the velocity was in common. That's because all of the velocity is tangential to those 2 shapes. So we'd have our velocity there, common between the 2. Now each is going to have its own omega, or angular velocity, about the center. And each would have its own radius, R1 and R2. But the common velocity there, omega cross r in each case, will be the same, which is what lets us set up those gear ratios. Now, when we think about the acceleration, however, what we'll see is that they have common tangential acceleration as well. So we're going to have an acceleration out here in the tangential direction that is equal to alpha cross r in each case. So we'll have some sort of alpha and a different alpha up here, such that alpha cross r in each case gave you the same answer. The difference is in a contact case is that this point is accelerating up on the top gear as opposed to this one accelerating down on the lower gear. And so we're going to have 2 different normal accelerations, omega squared times r, and a different normal acceleration of omega squared times r. So that's the difference between the 2. Velocity, it's all in the tangential direction, so we have common tangential kinematics. Acceleration, we only have that common tangential portion of the acceleration in a contact case. So with this, we've got the necessary theory in hand to approach a problem together. We have this idea of superposition of our translation and rotation cases to get a general case. We also have this idea of dependent motion for contact no-slip connections, which gives us common tangential kinematics such that the acceleration tangential and the velocity are going to be the same for points on both sides of that contact on each object. And with that, I look forward to working a problem with you. Thanks.